In this session, we'll be seeing AC analysis with Thevenin's theorem. Explaining to you two different types of problems. The first problem is obtain Thevenin's equivalent network for the terminals A and B in the figure. So here we have got the circuit with two terminals A and B. There is no load resistance connected, so we needn't remove any of the resistances. Okay, here we can see that since the terminals are open, there is no current flow through this terminal. That is, the current through this branch is 0. Therefore, the voltage at this point will be same as this point. Okay, therefore, the VTH we are going to find. VTH is the voltage we are going to find. The same voltage will be at this point also, since there is no current flow through this part. So we have to find the voltage across this terminal. Okay, the voltage, this is a simple loop, therefore we can find the voltage easily. When two resistors come in series, we can find the voltage across one resistor through voltage division rule. That is, total voltage into resistance of the same branch divided by sum of the resistance. Okay, here it is given 50 angle 0. 50 angle 0 means its rectangular form is 50 plus 0i. Okay, the complex part is 0, so we can take it as 50 itself. So we can find VTH is equal to 50 into resistance of the same branch, that is 4 plus 6j divided by sum of the resistance, 3 minus 4j plus 4 plus 6j. So we can put it in a calculator and we will get it as 2000 divided by 53 plus 1700 divided by 53i. Okay. And we can convert it into polar form using the calculator. Therefore, we will get VTH is equal to 49.52 angle 40.36. This is the VTH. So now we have to find RTH. RTH is the effective resistance on looking from this direction and by shorting the voltage sources. Therefore, we can find RTH as these are the resistances. Therefore, we will get it as 3 minus 4j parallel 4 plus 6j the whole plus 5 minus 4j, that is 1j. Okay, so we will get it as 3 minus 4j into 4 plus 6j divided by 3 minus 4j plus 4 plus 6j whole plus j, 1j. Again, we can put this in a calculator and we will get it as 256 divided by 53 minus 5 by 53i, and we can use a calculator again to find its polar form, which is equal to 4.83 angle minus 1.18. So now we have found the VTH and RTH. Therefore, we can draw the equivalent circuit as voltage source and impedance. This is 4.83 angle minus 1.18, and here it is 49.52 angle 40.36. That is the voltage source and VTH and the RTH. So now we'll move on to the next problem. The question is, find Thevenin's equivalent network across terminals A and B for the figure. Similarly, we have got two terminals A and B and there is no load resistor, and it is given Vx is the voltage at this point, and therefore we know that VTH is the voltage we have to find across these two terminals, and therefore VTH is equal to Vx. Okay. Also, since this is an open terminal, there is no current through this branch, and therefore the voltage at this point is same as the voltage at this point. Therefore Vx is the voltage at this point, and also we have got a dependent source which is dependent on the voltage at this point, dependent current source. Therefore we can find the voltage at this point, that is Vx, with the help of KCL. So we can write the KCL. Vx minus 5 angle 0. 5 angle 0 means 5 plus 0i, which is 5. Vx minus 5 by 1 minus 0.2 Vx is equal to 0. Current in this branch is 0. There are two branch currents. Sum of the two branch currents is equal to 0. And from this we can find Vx. That is 0.8 Vx is equal to 50. And Vx is equal to, sorry, it's not 50, it is 5. Therefore we can write it as Vx is equal to 5 by 0.8, which is equal to 6.25 angle 0. So now we have got the Vx, which is equal to Vth, that is Vth is equal to 6.25 angle 0. Now we have got Vth. So now we have to find Rth. For Rth, if there is a dependent source, the procedure is, for initially we short the two terminals and find the current through that branch. We short the two terminals A and B, short circuit A and B, and find the current through that branch, that is IN. That is the short circuit current IN, or we call it as short circuit current ISC. Okay, we find the short circuit current, and then with that short circuit current we have got we will find Rth is equal to Vth by ISC. Okay, this is the procedure if there is a dependent source. So now we will move on to find the ISC. So we can now redraw the circuit with the terminals shorted. So now I have redrawn the circuit. Here we can take a super mesh equation to find IN, or we can say that also one more thing is there. Since IN, there is no resistance across this path and IN is the current flowing through this branch, the potential across these two terminals is 0. Okay, since there is no resistance in this path, the current is flowing freely. Okay, therefore Vx, there is no potential drop across this branch. Therefore, we know that Vx is the voltage here. Therefore, we can tell Vx is equal to 0. Okay, and this current source is dependent on this voltage. That is 0.2 Vx is the current in this branch. Therefore, we can say this branch is effectively not present. That is 0.2 Vx is equal to 0. Okay, so effectively there is no such branch. You can exclude this branch and redraw it as this: 2, 4j, 5 angle 0 and 1 ohm. Okay, so now we have to find the current through this branch. So now we can write the equation for this branch as minus 1 into I plus 5 angle 0 is 5 minus 2I minus 4ji is equal to 0. That is minus 3 minus 4ji is equal to minus 5. That is I is equal to 5 by 3 plus 4j. So you can put it in a calculator to get it as 3 by 5 minus 4 by 5i. On converting it into polar form, we will get it as 1 angle minus 53.1. So now we have got the IN. IN is equal to 1 angle 53.1. Okay. So now we have to find RTH. RTH is equal to VTH divided by IN. And VTH we have got it as 6.25 angle 0 divided by 1 angle minus 53.1, which is equal to 62.5 angle 53.13. That is the RTH. Now as we have got the VTH and RTH, we can draw the equivalent circuit as VTH is equal to 6.25 angle 0 and here we have the RTH. RTH is equal to 62.5 angle 53.13. That is the Thevenin's equivalent circuit of the network. And here we have finished Thevenin's theorem and all the problems, all the sessions with Thevenin's, and next we will be starting with Norton's. Thank you. If you have any doubts, you can ask me.